Hey everyone! In this video I'm going to review some of the frequentist properties of OLS, and I'm going to explain why OLS, or linear regression, is sometimes described as the best linear unbiased estimator, or BLUE. And we'll talk about some other topics that we reviewed in the past, such as hypothesis testing and confidence intervals in the context of linear regression. Okay, so to start, just a quick review of the basic concepts of statistical inference that we talked about in the last week, as well as throughout the previous semester, for that matter. When we talk about statistical inference, we're always interested in kind of making inferences, learning something about data that we don't have based on data that we have. And in most cases that entails basically we have some sample that we collected and we want to make inferences about the population. But we can't observe the whole population, so we're trying to kind of characterize the population based on our sample. And of course we have to take into account the uncertainty around the statements that we can make based on that specific sample. Okay, so in this framework of statistical inference, trying to make statements about something we can't observe based on something we can observe, we work with estimators, which from the most general perspective, we can think of as rules, usually kind of mathematical rules, that connects our sample to the population, right? That helps us kind of quantify some quantity of interest in the population, and that kind of allows us to compute our estimator, or to make a statement about that quantity of interest based on our sample. Okay, an estimate is then a particular numerical value from a given sample, right? So the estimator you can think of as the rule, right? So kind of like computing the average, the way you compute the average, that's kind of the estimator, and the estimate is then one specific sample average that you computed based on your specific sample. Okay, and there are different characteristics of estimators and how we think of estimators as being more helpful or less helpful. In the frequentist context, the way we kind of establish good estimators is that they're unbiased, so they're true on average, that they're efficient, and that they're consistent. Efficiency means that they're comparatively have lower uncertainty. There's less uncertainty around a more certain estimator, or more efficient estimator is better than a less certain an estimator with more uncertainty. And consistency means as we increase our sample size, we get closer and closer to the truth. Okay, so those are all properties, desirable properties of an estimator that we would like to have, right? And it turns out OLS is an estimator that has, under certain assumptions, has these desirable properties, right? We also talked a lot about the central limit theorem, particularly in the last semester, which most broadly states that if we have a sum of independent and identically distributed random variables, then the sum of those IID variables, or the average of those IID variables, can be described or follows a normal distribution with some mean and some standard deviation. Okay, and based on that central limit theorem, we talked about kind of deriving test statistics, how we can do hypothesis testing, how we can compute confidence intervals based on this idea of repeated sampling. If we repeated our sampling procedure again and again and again, we could, and if our estimator is based on some, based on a kind of, for example, an average that is, obviously a sum of independent observations, then the central limit theorem applies, and we can derive our test statistics and kind of quantify the uncertainty around our estimates. Okay. Now, the next question is, of course, we're not only interested in estimating, average values in a population, right? Oftentimes, as social scientists, what we're most interested in is making inferences about associations between variables, right? So how is X related to Y? Oftentimes in the context of experiments, how does a certain intervention affect an outcome of interest, okay? And from the most general perspective, the way we can think about associations between two variables is to think about conditional distributions, right? And so here we have an example of a conditional distribution where we have different levels of x. We have on the x-axis here, we have different values of x, x1, x2, x3, x4, and so on. And we have here on the y-axis, we have different values for our dependent variable in this or we don't have to think about this causally, but the secondary variable, right? And so we see that for different levels of x, we basically have different conditional probability distributions for y, right? So that means there is some association, some kind of relationship between x and y, because depending on x, we have different conditional probabilities for y, right? So this is a kind of a very general way of thinking about how does x relate to y, right? We're not making any strong assumptions about the nature of that relationship. We're just saying, okay, conditional on x, there are different conditional probabilities on y, so to speak, okay? And now the way we think about OLS is basically, in this context, of course, we have no strong assumptions. These conditional probabilities for different levels of x have different shapes, different variances, some are just, kind of truncated, some are bimodal, some are, seem normal. Obviously the average value given x also varies, is not linear, right? So the way we can think of OLS and linear regression is thinking about conditional distributions and thinking about how x relates to y in terms of conditional distributions, but we have to invoke additional assumptions, specifically about linearity of the relationship between x and y and of the shape of these distributions across ranges of x. And we're going to come back to this and kind of visualize how OLS and linear regression kind of introduces some assumptions about the relationship between x and y in order to estimate our coefficients. Okay. All right. So one thing that we've done last semester is we walked through deriving the OLS estimator, both kind of for the simple bivariate case as well as for the multivariate case in matrix notation. Okay. One of the examples that we looked at as kind of a toy example was this study that looked at facial competence and vote share, where respondents in a survey evaluated the competence of candidates, unknown candidates, based on just their facial appearance, and then examined to what extent in a pairing of two candidates, to what extent candidates who were perceived to be more competent were also more likely to be successful in their actual elections. Okay, and that was one of our examples of kind of a bivariate relationship, which of course is not directly interpreted causally, but it nevertheless is an interesting relationship to examine. Okay. In general, if we kind of estimate a linear regression, the way we can think about this relationship and what the coefficient ultimately tells us is it tells us something about conditional expectations. Okay, so how does the average y vary with changes of x? Okay, so if we have a continuous independent variable, the regression coefficient tells us how much an increase of 1 unit increase in x is associated with a decrease or decrease in the expectation of y, or the average value of y. Okay, that again doesn't necessarily have to be a causal relationship, it's just a statistical association in terms of conditional expectations. Okay. We also talked about different ways of writing the linear regression model. One way we can kind of specify this, again here using matrix notation, is that y is equal to x matrix times beta plus epsilon, and we can, depending on our assumptions, for example, assume that epsilon that's the error term, comes from a normal distribution with mean 0 and some constant standard deviation sigma, or variance sigma squared, okay? The reason why we have this I or identity matrix here is because this is in matrix notation, okay? So this is a vector, this should have a vector indicator. This is a vector of error terms. It's not only one error term, it's a vector of n error terms, okay? Another way of specifying the same model is not just specifying the distribution of the error terms, but basically just saying, okay, y, the outcome variable y itself follows a normal distribution where the mean is determined by x times beta. So the mean mu is determined by the linear combination of the x's and the coefficients, and we have some, the error variance itself is then again the variance sigma squared times the identity matrix here, right? So in this case, it's the same underlying model, but we're specifying it as y, the outcome measure being drawn from a normal distribution. Here we're kind of looking at the systematic component and we're adding a normally distributed error term. But the point is, both are equivalent in terms of the underlying model that we're trying to describe, okay? And one thing we have shown, and this is again all a review from last semester, is that we can define the OLS estimator as minimizing, and it says here argmax. Of course, this should be argmin. I'm gonna fix that when I upload the slides. We're minimizing the sum of squared residuals, right? So yn minus beta prime xn, that's the residuals between the observed y and the y hat. We take the difference between our observed y and the y hat, that's the residual, we take the square, and we sum that up over all individuals, okay? So that's the sum of squared residuals, and if we minimize that, those sum of square residuals with respect to beta, so we find the beta coefficients that make the sum of square residuals as small as possible, that's our OLS estimator, okay? Because OLS, of course, stands for ordinary least squares, so we're minimizing the sum of squared residuals, right? That's what we did last semester, and we showed how we can derive the OLS estimator based on that definition. And we've shown, using matrix notation, that if we kind of just simplify this and find the minimum when taking the first derivative and so on, we can express the beta coefficients, the vector of beta coefficients in any regression as the following expression: x prime x inverse x prime y, right? So that is basically the result of this minimization procedure yields this formula that is just based on our data, on our x matrix and on our y vector, that will give us our vector of beta coefficients. And in the last semester I also showed you how we can kind of like manually program this in R and kind of confirm that that formula also gives us our regression coefficients. Okay, and we're going to go back to that example and kind of build off of that in the upcoming videos as well. Okay, so this is all a review of what we've done in the past semester. Again, as I mentioned in the overview video, feel free to go back to check out those videos again and make sure that you kind of follow all those basics that led us basically to this point. Okay. I'll take a quick break here, and in the next video I will talk a little bit about kind of beyond what we discussed last semester. I will talk about the properties of OLS both with non-stochastic axis and stochastic axis, and I'm going to explain why that difference is important in a second.